We're up to the official time for 126, and we've got a lecture to go through here. So it's a topic we've already covered in previous lectures in a cursory manner, but we'll go through it in a bit more detail, which is kernel debugging. So that's where we are. And then I'll do these projects 430 and 431, which are debugging with WinDbg preview. And they did need an update, those projects. I looked at them, and the second one I had to even change the flag because the previous flag wouldn't work. So it's good that I updated them anyway, and people who have been trying to work ahead and do them may have had difficulties. So let's start with the chapter, which is here. All right, so OllyDbg is the debugger we've been using for userland, which is fine, although it only does 32-bit userland code. It will not do the kernel or 64-bit code. WinDbg can debug userland or kernel mode bug code or 64 or 32-bit, so it's much more powerful. It's just much harder to use. So we're going to do some things with WinDbg. So you understand more of the structure of Windows here. Okay, device drivers allow third-party developers to run code in the kernel, which is a huge problem with the Windows operating system. There is code in the kernel that Microsoft did not write, and it keeps on crashing and causing a blue screen of death. And this very, very much irritates Microsoft because people complain and say this Windows is no good. And Microsoft says, we didn't write that code. So they've been more and more enforcing rules on third-party drivers that before you can put it in the kernel, you have to send it to Microsoft and actually pass some tests to make sure the quality of your code is good enough that it won't kill the box. So drivers load into memory, stay resident, and they listen for requests from applications. Your applications don't directly access the kernel drivers. There are these software structures called device objects, which I remind you, the general rule in all worlds of Microsoft is everything is always named the opposite of what it is. So a software object that has no material reality is of course called a device object, which would make it sound like a physical device. It's not. That is a software construct. So that's a software representation. So a driver creates and destroys the devices. When the driver loads, it creates a device, and a device is sort of the handle that a userland code uses to reach the driver to get to the hardware. So if you plug in a USB flash drive, the USB flash drive finds an appropriate driver, which is usually already present in Windows. Windows contains thousands of drivers built in, which is why stuff works easily. And then it creates the device object and assigns it a letter like F. Now your applications can read and write to the F drive, which goes through the device object to the driver to the hardware. If you plug in a second flash drive and it's the same brand, it would use the same driver again and make a second device object based on the same driver. And that's how plug and play works, which has been around since Windows 95 and is a big hit. It used to be every time you'd buy a printer or anything, they would have to give you a floppy disk or a CD with the driver on it, and you'd have to install that driver to use the printer. But then Microsoft invented plug and play, and a whole lot of drivers are just built into Windows already. So when you plug it in, it immediately just recognizes that it already has the driver, which is very nice. So remember DILs. DILs are like drivers, or at least they're often confused with drivers. So a DIL is loaded into a process. The DIL exports functions that your application can use in its export table. And when a function loads or unloads the library and a DIL is loaded, the first thing it runs is DIL main to prepare the DIL for use. We've been through that. That's what libraries do. Drivers are sort of the kernel analogous thing. Drivers are loaded into the kernel, and so when a driver loads, it runs the driver entry routine, which prepares it. And that prepares callback objects. And actually, someone says, I remember when you had to mess around with interrupts. Yes, I remember doing that too. I remember when years ago, when I upgraded, I think, to Windows 2000, I upgraded my machine, then I plugged in the printer, then I said, oh, bloody hell, where does the manual that I discarded like 6 years ago in a box somewhere so I can find out which dip switches to throw to adjust the interrupts? And then this box popped up saying, thanks to plug and play, your printer is ready to go. And I said, wow, that's neat. It used to be that every time you added a new device, you had to play with the dip switches. And the one thing I learned for all the cheap hardware I had is always the rules were always wrong. They had a chart telling you what switches to throw, and that never worked. So what you always had to do was just try numbers randomly until one worked. Anyway, yeah, now that's all automatic. Much, much nicer. All right, so a driver creates a callback object, and that's other drivers can request the condition defined by the driver and so on. So there's this thing called a callback object which is used to access the hardware through a driver. All right, so dills load into memory when a process is launched. Run dill main and go into the export table. The driver loads into the kernel when hardware is added, executes driver entry, and it prepares callback functions and callback objects. That's how the two compare. So driver entry, dills expose functionality through the export table, but drivers don't. Drivers do it with driver entry. Driver performs this registration for the callback functions. It creates a driver object structure, and then driver entry creates a device, which is what you see on userland. So here's a normal read request. Your user mode application obtains a file handle to a device, calls read file. The kernel processes the read file request and calls the callback function, handling I/O, which actually connects to the hardware device like a hard drive and reads something and passes it back up the chain. So for malware, they often use device I/O control. This is a generic request. And remember, the normal programs would use read file. This is very much like the internet thing we've talked about in the past. There's a handy high-level call, which a normal author would use, but a malware author will typically use the less convenient low-level call, like device I/O control, which can pass in an arbitrary bunch of data and get an arbitrary bunch of data back. So this can do read or write. So here's how it all looks. You have your program here. It calls, remember, kernel 32 is the library you are supposed to use to manipulate the kernel. And then it calls ntdill, which is the native Windows. This is the Windows API. This is the native Windows API. This is part of the Windows API, to be fair, but this is the native API. That then goes to kernel mode and calls ntos kernel, which is the kernel itself, and the kernel goes through a driver to data structures and eventually to the hardware. So that's the game. All right. And there is some malware in the kernel that lives entirely in the kernel and has no user mode component, although that is probably not true for modern versions of Windows because kernel mode rootkits are almost extinct as far as I can tell. I certainly was unable to find any hands-on projects anymore worth doing where you can play with kernel mode rootkits, and if anybody finds any good ones, let me know. Microsoft has really tried hard to wipe them out, and as far as I can tell, they pretty much succeeded. They were all the rage in Windows 2008 and XP and such, and Microsoft got fed up with it and improved their security, and that appears to have worked. So ntos kernel and hal.dill are used. ntos kernel is the Microsoft kernel, and hal is the hardware abstraction layer that is sort of like a driver for the basic hardware, like the main chip on the motherboard, the firmware on the motherboard, and the processor and such. Anyway, malware will import functions from one or the other of these libraries to manipulate the kernel. So I've got a Kahoot about that stuff. Yeah, let me get rid of some of these tabs where I was trying to debug the project. All right. I finally had to remove a step from one of the projects because it just doesn't work anymore as far as I can tell, and there is no fix that I could find. So it reminds me that we're using beta software. When you're using WinDbg Preview, it isn't guaranteed to work or to keep working the same way, and it no longer seems to work the way it worked 6 months ago. All right. Good. There may be only 4. Looks like it. Okay. Okay, what does an application interact with? It interacts with the device object, not the driver. The device object is what it reaches in user land. All right, what code loads into a process? That's a DIL. Good. Libraries load into processes. All right, when a driver loads, what procedure is called? Driver entry. Good. All right, and which one of these runs in user mode? The kernel 32, remembering the fundamental Microsoft rule that everything is named the opposite of what it is. Kernel 32 is the user land component that leads to the kernel, which is elsewhere. All right. All right. Good. I know who those people are. And I think I know who that person is. Good. Good. All right. I shouldn't have closed the other tab. That'll do. All right. Okay, so kernel debugging. Now, in VMware, you can actually do kernel debugging between 2 virtual machines, and my students used to do this maybe 6 years ago, and it's miserable and doesn't work very well, and I'm not doing it in this class anymore. But you can do it. You configure a virtual serial port between 2 virtual machines, and then you control one machine with the other, and it didn't work very well. In the book, they use boot.ini because your book is really old and refers to Windows XP. Next semester, I think I found a better book to use. Anyway, nowadays it's bcdedit. This is how you prepare your machine for debugging. You do bcdedit/debug on, and that's what we do in the projects. So you install WinDbg from Microsoft debugging tools, and then you got WinDbg. It gives you a lot of tools. You can just choose debugging tools for Windows and not bother with anything else, and then it's not a very big download. And you can run LiveKD, and we talked about this one before. LiveKD is the original sysinternals tool that lets you basically perform a crash dump of the operating system and look at that in the debugger. Although I think he doesn't actually create the crash dump, I think he somehow fools the debugger into thinking it's looking at a crash dump, but it does give you read-only access to the kernel on a live system, which is nice. All right. And so now you got to learn these command line commands, which I think we've already talked about in previous classes and project demonstrations. So D will dump contents of memory. DA will display it as ASCII. DU will show it as Unicode. DD will show it in hex as 32-bit words. And DA, so DA here would show the ASCII text starting at that address. There's also DB, which will show it as ASCII and hex. All right, then you can edit memory with E. I've never used this, of course, because you can only use this if you really have two machines connected together. And I have a project like that that runs in Azure, where it's pretty easy to set up two machines. But I'm not demonstrating that one tonight. I think it's still in the class, though, someplace in the extra credit. You can actually edit the contents of memory. And you can use all plus, minus, divide, multiply. You can, this will reveal the value at a 32-bit location. And so this would show you the first argument for a function. Go to the stack plus 4. Remember, when you call a function, the arguments are sitting on the stack. So you could see the contents of a stack here. And you can set breakpoints with B, although again, only if you really have two machines, one controlling the other as a slave. If you're doing it in the kernel. We're going to do it today in userland, which is okay, but you can't put breakpoints in the kernel without two machines. And so G starts the machine running, the debugged program running again, and you can use expressions. So this will get process address here. When that's called, when it gets there, it will break, and then it will print out in ASCII this value. And this is something that I think I use to show every file that's opened. You can make a loop. So you can really write little scripts in WinDbg that do all sorts of great things, like print out the name of every file that opens. You can really duplicate the API monitor, which we had in an earlier project, where you just choose API calls and you want to print out the arguments of those calls. You can do all that in the debugger with commands like this and make things that will trace calls to API, various API calls, and see what they do. It's really very powerful, but you do need to learn to write these sort of scripts in its language. LiveKD, of course, is read-only, so you can't use breakpoints. You can't stop anything. You can list all the modules with LM. This will show you the exes and dills in user space and all the kernels in kernel mode, depending on which mode you're in. And I think I now understand this better. In Ollie, we used memory map, and memory map showed exactly what memory regions were set to every userland process. And you don't see that in listing modules, and this is where I think I finally understand something people told me 10 years ago when I found an exploit that would crash Windows. They said in kernel mode there is no memory control. Processes don't have their own memory region, they all just share memory. So if one of them hogs up too much memory, the whole thing just dies. There isn't a memory map of using memory in the kernel, not in the usual sense. And I guess that's true. Now, I'm a little confused how that would work. And in fact, it does crash for strange reasons, but they say they do that to make the kernel fast. So this will show the disk driver, where you'll list modules for a module named disk, and then you see the driver for the disk, which has a symbol path called disk.pdb. PDBs are the symbols, so you can see the names of variables and routines in that executable, and we'll play with that in the project demo later. So this will show the start of the NTOS kernel. NT is the one that has a shortcut for its name called NT. This will show the first 10 words of the NT module. So here's DDNT. It shows whatever the default number of words is, and here you specify to give me 10 words, and this 10 is hexadecimal, so it is 16 32-bit words, 4 on a line. You can see them here. All right. .hh shows you help and takes you here, and the online help is very powerful of this thing here. R dumps registers, and off you go. So, all right, let's try another Kahoot. 10b. Good, that may be all we're getting. I'll give it a few more seconds. So to set a breakpoint, what do you do? Good, BP. That's an easy one. All right, showing memory as ASCII. Display as ASCII. All right. And which one shows kernel drivers? Yep, loaded modules. And which one changes memory? Ed will edit a double word. All right. All right. All right, I know who those people are. And good, we're on track to keep going. Okay, so Microsoft symbols, I mentioned these before. If you have a symbol file, then you can use descriptive names like the name of an API call, like create process address space, instead of having to know the hexadecimal address of that module on your system. So you can search for module name, symbol name if you have symbols. All right, you can look for names associated with addresses. Now NTOS kernel, you can use the shortcut NT. So NT bang, NT create process is an address. You could as well put a hexadecimal value if you knew it, and now you can unassemble that function by just referring to it by this descriptive name. So we've done these before. I'm not going to do them live. You can unassemble it, and then this will get you the whole function. You can also look at just the first 10 or the first 20 words, I think of it, this way. All right. You can use BU to set a breakpoint on a function as soon as that module is loaded. So it will remember that you want to have a breakpoint, and if that module is not loaded now, it'll wait to see if it does load. This is a function that finds the entry point of a module. So you can set a breakpoint on the entry point of a driver, and then when that driver is loaded, it will break, which is kind of nice. You can search with X. X is examine. You can examine, we did this before, NT bang star would give you all the NT functions. NT, and this is a pattern to match, so it gives you the functions that contain create process in them, and there's about 10 of them. NT create process and ZW create process and a bunch of others. You can, if you see a jump that jumps to an address and you don't know what it is, you can look for the closest symbol near it to get a clue. So I have this address, I use ln to find the closest named object, and it finds, this is 805717A, it finds there's an exact match at NT read file, and there's another one after it, NT real file scatter. And here's the exact match. So that was a particular exact match. If there wasn't an exact match, it would still hunt and find the nearest symbol, which would give me some clue what module am I in, what's going on here. All right. DT lets you display the type information about something. So you can display any amount of structures. I mentioned this before. This is why Microsoft cannot hide what the kernel does. There are undocumented functions, but you can just figure them out by using the debugger. And you can either look at the structure of a data structure, or you can fill in data from this area and have the structure of a data structure and the specific values for one instance of it that's in use. So here is the structure of a driver object. And this is just the C++ type data structure where you have something called type that is an integer 2b, which whatever that is, 2 bytes, I think. Yeah, 2 bytes, you see it's 2 bytes here, then the size, then a device object, which is a pointer 32. Then you have down here a Unicode string for driver name and so on. This just tells you the names of the various attributes of this data structure and what type of data and how big it is. Or instead of just doing dt nt bang driver object, you could give it dt nt bang driver object and then the address of a real driver object, and now it will show you the relative location, the name, and the actual value of these things. So when you go down to driver name, it will show you it's a Unicode string, and there's what it is. They've loaded the contents of the beep driver. So that's kind of nice. All right. So driver init is called when a driver is first loaded. And you'll see it here. Driver init is part of the data structure. So there it is. It gives you an address to run when this thing is loaded. And you could put malware directly in there, just like when we made a malicious DIL with Metasploit earlier. It just put the malware right in DIL main. So as soon as it's loaded, it runs the malware. You could do that with a malicious driver. You could just put the malware right in driver init. And then when it loads, it'll run your malware right away. So for Windows system structures, like all these NT ones, you need to have Microsoft symbols, and you can just specify in file symbol path this, and it will automatically download them from Microsoft as needed. And I haven't checked. I imagine this is the default in WinDbg Preview because it just seems to happen without any need to worry about it. You can also manually download the packages for every version of Windows, and you have to get it for exactly your version, even down to the minor version number, which is like how many updates and patches you have, or the symbols won't be accurate. It's nice that it does it automatically these days. So let's find the cahoots. All right, where are the cahoots? Perhaps I'm running them in a strange browser. Oh, I'm running them in Firefox for some reason. Well, anyway, that'll do. All right. I launched them in some window I had open without paying attention to which browser it was. That's probably why it gave me a strange problem logging in. Okay, anyway. All right. Aha. The population has increased. All right, let's give it a try. All right, to set a breakpoint. That will make a delayed breakpoint to go to the starting point of the FastFat driver when it loads. And I think the FastFat driver is for a fat device like USB drive, but I'm not quite sure what it is. All right. All right, which one shows the type information for a structure? DT, display type. That shows you the structure of the data structure for a driver object. And how do you get all the functions in NTOS kernel? Yep, that's examine, and this will give you all the symbols in NTOS kernel, which will include all the functions. All right. All All right, we got repeat winners here. Whoops, that's a 9. All right, that's a 9. There we are. Okay. All right, good, and we're right on time here. We can keep going. Back to here. Okay, so in practice, here's a program that writes to files from kernel space, which is not what you normally do. So a kernel mode program cannot call user mode functions like create file and write file. It has to go to nt create file and nt write file, which will be in the kernel, which is where these other functions would eventually go. So you can have user space code to load a kernel driver. This creates a service down here, calling the create service function. And all the rest of this is just setting the parameters. And here's like service type 1 is a kernel driver. So this is user space code that will call this API call, which will create which will load a kernel driver. And now you obtain a handle to a device object. So you're going to call create file A, and that will give you the handle. You have a file name here in EDI. This points to file writer device, and these are the other parameters. So you call it, and then it will return a handle to it, probably an EAX, I imagine. That's where function values typically come back. Once you have a handle to the device, you then use device IO control to send data to it. So it's going to call device IO control, and so up here it's going to have the number of bytes returned, the out buffer, the in buffer, and some kind of control code, and a handle to the device, and off it goes. So this will send some data to the device and receive some data back. So in kernel mode code, you can see all the loads of objects in the kernel, and you shouldn't really be seeing kernel modules load or unload unless you're plugging in USB devices and unplugging them or something like that. So if some things are loading, they're probably malicious. So this is a thing called filewriter.sys, which is a piece of malware loading. One exception is kmixer. Kmixer.sys is something that VMware loads and unloads frequently for some reason, so that's not malicious if you see that. I don't know what it does, but it's apparently part of VMware. This is something to remember. VMware is a simulated hardware, and it's really not very hard for you or for malware to tell that it's in a virtual machine. And an ever-increasing amount of malware knows when it's in a virtual machine, and it will not display its proper behavior there. So dynamic analysis gets harder with more modern malware. So bang dir obj will show you a driver object. This will show me the file writer driver object. And off it goes. Notice it could not find the symbols for filewriter.sys because it's not a Microsoft product. It didn't find it in the online Microsoft library of symbols. So you're going to see the code, but you're not going to see the symbols. You won't have names for variables or functions. So DT will show structure for a driver object, and you can see what's loaded here. Here's the file writer driver displayed this way. You can see there's the Unicode string, and other things should be here, like the start address is here, and so on, and the size. All right, so it eventually creates this file. This is how you refer to an object if you, not by a drive letter, but by a fully qualified object name starting with the root device of DOS devices, then drive C, then secret file. So this is typical kind of thing malware would do, put a file in a sort of unfriendly place. All right, so applications work with devices. They don't work with drivers directly. So if you look at the user space application, you can find the device object. That will then find the driver object, and you can use device object to find out more about the device object and handles to find more about the applications that use it. So you can view the userland code from WinDbg also. And then we can talk about rootkits, which, as I mentioned, is really of historical interest. What we're saying here, this is no longer possible in modern versions of Windows, but this is how they used to work. The point of rootkits is that they would hook processes and API calls to fool your system, sort of like making it into a virtual machine. So when your system would try to do something like a virus scan, it would try to list all the files and folders and then scan them all, but the rootkit would hook the calls to like find a file and open a file, so the antivirus would not find some of the files. It would think it had scanned the whole disk, but it hasn't because the API calls have been hooked. That's how it works. And so it can hide running processes, network connections, files and folders, or anything on your machine so that you can't see it from the Explorer window or from the command prompt, and your programs running, like your antivirus, can't see it. So this is why this has been described as the blue pill, is what a rootkit that Joanna Rutkowska wrote, where it turns your machine into a virtual machine and you don't know it. And now there's other things happening that you can't see. So the way it was done was with the SSDT table. This is the System Service Descriptor table, and it is was used by a lot of security products like antiviruses and firewalls, and by rootkits. The purpose is, this is Microsoft's internal table to lead to function calls in the kernel. And you're not supposed to mess with it, but everybody did. One of the many things that irritated Microsoft. Now, if you're in user land and you want to access kernel code, you do it with one of these commands that all do essentially the same thing. These make the jump to kernel space. You syscall, sysenter, or int2e, and then you have parameters in the registers like EAX that tell it which kernel function you're trying to access, and off you go. Sysenter is the modern way to do it. Yeah, the other ones are older ones. Anyway, so here's ntdil. So it's going to call ntCreateFile function, and what it's going to do is just prepare some parameters and then call sysenter. So it's just putting stuff in the registers. 25 is going to be the code for create a file. Then it runs sysenter. It'll then call ntCreateFile. This is how you do it. All right. And what it does, though, is it does not jump directly to the kernel structure, because suppose you wanted to put on a Windows update that would change the kernel, then all of your previously compiled user code would have to be recompiled, and that's not the case. So when you call a kernel mode function from userland, it calls it kernel mode function number 25, and that goes to the SSDT and finds function number 25, where it finds a pointer to the function. This is also in the kernel, so if you put on a Microsoft update that changes a kernel function, it will just change this number to point to where the new function is, and your userland code will continue to work as before. That's the point. This is why you see these indirection tables everywhere in computer programming, to solve that purpose. It makes it possible for one end of something to be updated without updating the other end. But it does mean that this is the place to hook it. So the clean SSDT, all these addresses are pretty much the same. They all start with 805 or 806 on this machine because the kernel is actually not very big. So addresses in the kernel are all in a pretty reasonable small area. They're all going to be in the same range. So to hook it, you change that number to point to your malware, and your malware will now read the file name, for example, and if the file name has a special character in it or something, it will not process it normally. Otherwise, it will pass it on to ntCreateFile, and that will hide anything that's using ntCreateFile. But the directory function in the command prompt doesn't use ntCreateFile. It's going to use something like ntReadFile, so you would have to hook more than this one function. And simple rootkits hooked like maybe 10 functions. So you can just look at the SSDT and you'll just see it. You'll see addresses there that are not in the range to point to the kernel. They point somewhere else. It's incredibly simple. All right. So here, for example, I used Windows 2008 VM for this stuff. Here's the kernel service table, and you see they all start with 82. So these are all clean, real kernel calls. Nothing wrong with them. I had to use this longer command on my Windows 2008 instead of the short one in your book. There are different versions of it, but that's the SSDT. This is the start of it. It's much longer than this, of course. It has hundreds of functions. But if you hook it, if you just print it out this way, you'll see they're all 80, 80, 80, but this one is different, F7. That's the one that's been hooked. Instead of pointing to the kernel, it points to some other function. That's what the hooks look like. Is this why persistence on the WinOS has moved to the registry since you have issues with rootkits? No, I don't think so. There have always been registry and many other persistence methods. There's a lot of persistence methods. You can use the registry, you can use the startup folder. if you use the sysinternals tool, auto runs, it'll show you. There's about 60 known auto start extensibility points on Windows. Putting code in the kernel is not a way to make it automatically start. You would also need to have like a registry entity. It's just the point that it runs at high privileges in the kernel. That's a good question. But the kernel's not really for resistance. The kernel's just to run with high privileges. And a really good rootkit was essentially undetectable and unremovable. That's why they were really pretty dangerous. And Microsoft got rid of them because they're envious of Apple. See, there are no rootkits on an iPhone because when you boot up an iPhone, it checks a signature, a typical X509 certificate on it, and it checks the hash value of the operating system before it loads it and compares it with the online verification procedure. And if it does not find kernel code that is signed by Apple with a valid signature, it won't boot up. And Microsoft added that feature in Windows 8, and they're increasing that kind of security on it. So it is entirely possible to require the kernel to be clean or not boot up. And Microsoft is moving in that direction by imitating Apple more and more. They can't do exactly what Apple does because they got sued by antivirus companies saying you can't prohibit us from putting functions in the kernel. If you do, you're destroying our whole business. So Microsoft no longer knows exactly what should be in the kernel, so they can't make sure the kernel is 100% clean. But they have moved in that direction to where it's quite impractical to make kernel mode rootkits as far as I can tell. Anyway, so you can find a malicious driver. In the kernel, everything is drivers. LM will list them all. And you see the address for them too. And so anyway, so he found a function. I'm not sure I can see. Here's the rootkit, I guess, but I'm not sure I can see with the address here. Anyway, you find it, then you can list its function. And what you see here is it's going to call ntCreateFile. Now it hooked ntCreateFile, but what it does is it checks first. It does some kind of call something in a test. So it calls some subroutine, which will somehow decide whether it wants to let you see the truth about this file or a lie. And so it checks to see if this is one of the files it's supposed to hide. And if it is supposed to be hiding it, then it goes down here and loads this code which says file not found and returns. Otherwise, it calls the real ntCreateFile, which will make it. So that's what it does here. All right. Anyway. So interrupts are another way to do it, and you can register a handler for an interrupt, and that will call an interrupt service routine, and it will go through the interrupt descriptor table, which is just another table like the SSDT. So you can also connect, put malware in the interrupt, and here's the IDT showing various things. APC interrupt, which is something to do with power on and power off, and USB port interrupt. I guess this is what detects that you plugged in a USB thing, and therefore it's time to load a driver or something. Something about the mouse and keyboard interrupt, noting human, so on. These are all the various interrupt signals that happen when things happen, like the user doing something that you should stop whatever you're doing and go process that keystroke or something. There's a thing called the OSR driver loader tool you can use to load a driver to test it. And like I say, this is why that stuff is all pretty much just historical, because 64-bit Windows and the later versions of Windows, Microsoft improved stuff. First they got rid of boot.ini and moved to bcdedit, and then they added patch guards, so third-party code cannot modify any part of the kernel, like the SSDT or the IDT. So you can't hook those functions anymore, and that seems to be working pretty well. And they enforced driver signing, so only digitally signed drivers will load. And that means that kernel malware is practically non-existent. I think there have been a few cases where the malicious malware authors actually managed to steal or purchase a real code signing signature somewhere. And there are a few cases I've read about where they found a commercial product with a driver that had a security vulnerability, but it was signed. And so they will actually install a pirate copy of that commercial product to get the bad driver in there and then exploit the driver through a weakness in the driver. But there's always some way around it. But it's gotten much harder, and you can't just hook the SSDT anymore. You have to use much more indirect ways to get into the kernel. All right, so let's look at the Kahoot here, which is 10D. right, there might be one more, but apparently not. All right, so what module does VMware load and unload? K-Mixer. All right. All right, what's the function that Microsoft components use to execute kernel code? That's SYSENTER is the modern way to do it. These are the old ways, syscall and int2e. They all accomplish very much the same thing. There are very subtle differences. I read a couple articles about it, but I can't remember the difference. Nothing too important. All right, how do you normally put a rootkit in, back when you could do it? In Windows 2008, say. Yep, the SSDT hooking. All right, and which one of these is not in Windows 10? boot.ne, that's been gone since Windows XP. And if you want to use unsigned drivers in 64-bit Windows, what do you do? You set no integrity checks with bcdedit and boot up in a special mode, and then it will allow you to use unsigned drivers, which is something you'd only do for testing these days. All right, so it's just about 7. Let's stop until 7:10, and then I'll demonstrate a couple of these debugging projects. So I'll be back.